before they come here. So, hi everyone, my name is Martin Demeter, and thank you for the opportunity to presenting our results, and thank you, the audience who came here for listening and discussing the topics. I'm presenting on behalf of Chimera Solutions, a startup where we are solving real-life problems using AI, software architecture, design, and data science tools. We partnered with OMNeT++ team, and the story of our collaboration will be a topic for today's presentation, which is the inference of packet error rates using snare patterns via neural networks. So what are the beginnings here? Long story short, at 2020 OMNeT++ Summit, where I was not present, but I got the slides from it, there was a proposal from OMNeT++ team, which I just copied over here, which are the future remarks that someone knowledgeable about neural networks could produce great results in a short time regarding their project. And then, long story short, in 1 or 2 months ago, I don't remember exactly, we met at Upwork, because we are on Upwork as well. And then our story and our collaboration began. So what is the problem statement here? So basically, our main goal for this collaboration was quite straightforward and easy to understand. We wanted to improve the speed of current Wi-Fi error models with neural network approaches, while we also maintaining the baseline accuracy of these models. I'm going to talk about later what are these baseline accuracies or models are. But first of all, there are going to be some definitions which I'm going to use during the presentation, so I should outline them to get into the same picture. So what are these snares? These are our inputs. This is going to be our inputs to the neural network. And the definition of it is commonly used in wireless communication as a way to measure the quality of wireless connections. The error model, which models we want to enhance with neural network approaches, they describe how the snare affects the amount of errors at the receiver, the Wi-Fi receiver. And there are these packet error rates, or PERs for short. This is going to be the output of our model and also the other models what OMNeT++ using. And it's used to test the performance of a receiver. Basically, a PER is the ratio in percentage of the number of test packets not successfully received by the receiver. So these are definitions what we're going to work with. Yeah, I'm going to mention throughout the presentation some models which are currently being used and the neural network approach as well. So there is currently used by OMNeT++ team the scalar radio model, and highlighting the color is also important during the presentation. So the scalar radio model is based on analytical formulas. It's based on just single snare values, and it's very fast, but it's quite inaccurate. So for some scenarios it's useful, but most of the scenarios is just too inaccurate. There's the layered radio model, which is going to be acting as a baseline throughout this whole project and during this presentation, because we are lacking of empirical data. I mean by empirical data that we don't have real life data coming out from Wi-Fi network sending packages from A to B. And that's why there is this layered radio model, which is based on the whole snare patterns. I'm going to talk about later what are these patterns. And it's quite slow, but it can be trusted as a baseline. And we're basically training the neural network by data coming out from this layered radio model. And there is our neural network approach, or basically the neural network approach, also what OMNeT++ team tried to propose. So why we want this neural network approach? It can be quite accurate, it can achieve very fast inference speeds, can generalize for different Wi-Fi modes, and can take into account the whole snare pattern by design, because these neural networks are used for being very good with recognizing high-level, high-dimensional patterns in data. So what is the pipeline here? So there is the layered radio model, which outputting data, we're creating training and testing and validation data sets out of it. Basically, the data is nothing else but the snare patterns and these packet error values corresponding to each other in pairs. There's the neural network, what we're creating. We train it, we export the network weights, and we're going to use them, or basically OMNeT++ team is using it or will be using it, hopefully, in the existing OMNeT++ pipeline. And one of the, or if not the motivation of this whole project and presentation, is to achieve this trade-off what I outlined you here. So there is computational time in the horizontal axis and accuracy. I'm going to talk about more what is accuracy in this case, but basically accuracy is how close you can get to the layered radio model baseline, because that's the etalon here. And what we can see is that the scalar radio model is not quite accurate, but it's fast. The layered radio model is quite accurate, so it's the baseline, and it's pretty slow. So we would like to create a approach with neural networks which can get very close in this so-called accuracy to the layered radio model, but can get very close in speed, in computational time, to the scalar radio model. So this is basically our goal to achieve. So in our opinion, every data science project should start with data exploration, getting familiar with the data, interpreting it, understanding it, cleaning it, reinterpreting it, or even re-representing it if necessary. So we really think this is our core idea, that you have to get familiar with the data first. So what is our data here? Basically, what we got as an input data is a tabular data, where you can see the packet error values corresponding to this time division and frequency division values. I'm going to talk about here what is that exactly, and the snare values. So the snare pattern, what I was referring to, is basically this image-like data. So these are in these bins all the snare values. I also copy-pasted it from that 2020 summit, so thank you for this picture. And there is this time division, which tells you how many lines this image-like snare pattern has. And also there is a frequency division when you slice it up into frequency domains as well. So this is our input data, basically. We design a neural network. So this is, again, the pipeline. We input this snare pattern somehow, like in an 8x52 image, for example. And then it's going to infer us one single value from 0 to 1, a float value, which is the packet error rate. This is the whole thing what we want to create with the neural network approach. So still we are exploring the data, and I'm offering you now a conjecture. If humans can recognize relationships between packet error values and these snare patterns, there's a great chance that neural networks can do also, and even doing it better. So this is our conjecture, and we're trying to test it here. But most of the time, this as a rule of thumb, it works. So that's why we said it's going to work here as well. So now I'm representing this schematic figure with these 3D plots. So these are the snare patterns, again, with frequency and time division. And what you can see and what you have to understand here, that if I'm increasing the packet error rate, if the packet error rate is increasing, then what you can see for smaller values, the pattern is basically homogeneous. And then as you approaching higher and higher PER values, you can see greater and greater inhomogeneity is rising. So we have a clue now that what causing the packet error rate. But of course, we are not that good as machines in interpreting high-dimensional data, so we are going to offer this to the neural network. So I created an interactive collab notebook where you can try out for yourself, if you want, that how you can recognize these patterns. And also there's an interactive 3D clustering demo where you can go through, like in an interactive gallery, and check for yourself these clusters where the data is clustered into this with respect to the PERs and these snare patterns, just to check it for yourself how the conjecture works. So let's jump into the methods. If you don't have any question, maybe you have. I heard something. Excuse me.
I just pasted the links for you in chat.
Oh, okay. Thank you very much. Yeah. So if there is no questions, I'm jumping straight to the methods, what we tried. So there are different types of topologies and different type of neural networks architectures what we can try for this type of problems. So first of all, because this is an image-like data, it's straightforward to think that, yeah, for sure, convolutional neural networks could do the trick. But keep in mind that we cannot create really, really deep networks here because we want to reach blazingly fast speeds. So we cannot just create really big like ImageNet-like networks because they're not going to be that good to train, or in inference speeds they can be quite bad in this case. So what were our expectations? You have to know also that the input data was variable. So in the middle of the project, as I remember, we realized that the input data is not going to be fixed in size. So I mean fixed in size by the shape of this data. So we realized that one of the dimensions is going to be variable. But we said that, okay, it's also compatible with convolutional neural networks because they are compatible with different input sizes. It's not a problem for convolutional neural networks. These are excellent in image-like pattern recognition, but they have also a really big limitation, which is our conjecture here again, with regarding the CNNs, that these are limited in long-range interactions in the data. What I mean by this, for short, but I'm going to give you some idea later on in an article, what you can read at home if you want. That it means basically that when convolutional neural networks, especially shallow networks, are trying to recognize patterns, they do it more locally. They recognize local patterns like eyes by itself or small parts of the image. And they basically, most of the time, just losing some information, which can be, in this case, very valuable to us regarding this data, what we have now. So in reality, we tried it, but because of this locality issue, with this lacking of long-range interaction recognition, it was not we were not that satisfied with the outcome of CNNs. At the very beginning, we also tried XGBoost just because it's the state-of-the-art method for inferring tabular data. And of course, the limitation was very straightforward. The input can be fixed. So for XGBoost, the input should be fixed all the time. So we just had to just throw it to the dumpster, really. And then we converged to LSTMs. I'm going to outline why LSTMs are a really good solution here, or a type of neural network for this case. And also, it's really interesting because before this presentation, I went to the OMNeT++ 2020 Summit presentation as well, and they also outlined the LSTMs as a possible solution. So it was quite funny that we both converged to this idea independently. And so why LSTMs? These are long short-term memory neural networks, and they are a type of recurrent neural networks, and they are really good in time series data recognition. So all those types of data which requires long-range interactions to be recognized. Basically, this type of network satisfied all of our expectations regarding this project. There is one small issue, but in this small networks, I'm going to show you the configuration as well. It's not that big of an issue that the training time is a bit longer due to the more sequential structure of these neural networks than, for example, for CNNs, because they can be parallelized with GPUs much more heavily. So this is a bit crowded slide. We can discuss it more in the questions if you want, but this is basically the structure of the neural network, what we created. It has just 64,000 parameters, which is quite a few parameters. So the bottom line is that this is a quite lightweight and fast network. We can input this variable input size data to the network. It's varying in time division with regarding to time division. and we can input it in batched ways, so we can input more than one altogether, more than one input once to train. So again, we have this conjecture why the LSTMs are better in these long-range interactions, but there is a great analogy here, and I highly encourage you to read it home if you want, or after the presentation. So the analogy is that there is a study where they're inferring protein 3D structure from amino acid sequences, and amino acids, because amino acids sequentially can be close to each other, these amino acids in the sequence, but it doesn't mean that they are close to each other in 3D space, because when proteins are folding, these sequentially closed amino acids can be very far in 3D space. So long story short, these networks can be really good in this type of models. And I also outlined here a CNL locality issue that you can find. So after we designed the neural network, we wanted to integrate it. And basically the integration part was mostly by the OMNeT++ team. And what they did is that we created this Python and Keras implementation of the neural network, and we exported the network weights. And with this really great tool, which I highly recommend if you are into these topics to check this out, it's just incredible how good it works. It's frugally deep repository, and you can just convert basically to a format which can be used in the existing OMNeT++ pipeline. It's going to be compatible with C++ pipelines. So the results, yeah, we can start to investigating what was the results. So here we trained the LSTM network on approximately 160,000 lines. We split it into training, test, and validation sets, and there was about 15,000 lines of validation data, if I remember correctly. So the input size was the batch size times the time division and frequency division. And what we can see, figure on the left, is a comparison of the distribution of both the predicted and the target data. And what you can see is it's quite in a good agreement. Of course, it's not a rigorous comparison, but if we compare it in this way, and with the figure of the right, where we plotted the predicted data in the function of the target data, which is this correlation type of plot, you can see that the correlation is quite high. It's about 0.99, and the root mean squared error in this data is 0.06. So these are quite satisfying results. So, but we have to go a bit further, because in this type of simulations, what OMNeT++ team using, there's a lot of parameters where you can play around with. For instance, there are these several simulation parameters like noise duration, noise power, number of noise sources, message length, and so on. So for better understanding, we created a metric for the noise, which is just multiplying the noise duration with the noise power and the number of noise sources, is going to create a microsecond times milliwatt quantity. And all you have to just understand that as we increasing the noise, you see the three models, the scalar radio model, the neural network, and the layered radio model plotted. So here the horizontal axis is the number of noise sources, and the vertical axis, which is important here, is the percentage of received packets. So basically this is the inverse of the packet error rate. So if it's 100%, then you received all the packets. If it's 0%, you've lost all the packets by the receiver. And what you have to see also is that we want to get as close to the baseline, which is the green line here, with our neural network approach. So here, if you increase noise, you see that the pattern is changing. Of course, if noise is increased in the environment, it's very hard to get to receive the packets correctly. So you see this trend here, but more importantly, you see that our neural network approach is quite confidently recognizes this pattern here, while we changed a lot of parameters altogether. Another interesting plot here is that when we plot in the horizontal axis the message length, which is basically in bytes, so how big is a message, what we want to send and the receiver want to receive. And in the vertical axis, you see the runtime in milliseconds. And what you see here is that the scalar radio model's runtime is really close to the runtime of the neural network approach, while the layered radio model has a significantly longer runtime. So here, what I propose that our main motivation to be in so-called accuracy, we are quite close and we are quite goodly interpreting the baseline with regarding of accuracy. And with regard of computational time, we are quite close to the scalar radio model. And now we incorporate all this data into two heat maps. So basically what you can see here is, again, the message length and the noise metric. And here I just plotted the difference, basically, excuse me. So the difference between these values plotted in this parameter space, what you can see in the heat map. And what you see here is that for this large parameter space, there is really small differences between the neural network approaches values in packet error rates and with regarding the baseline layered radio model. So here we outline that we are quite close in so-called accuracy, or we are really we are nicely mimicking the layered radio model. And also what you can see here is the message length again and the noise metric. But now I plotted here for every cell that what is the ratio between the layered radio model's computational time and the neural network approach's computational time, which basically tells you the speed up of this whole, the speed up of the neural network approach. And this is basically, especially if the message length is large, then you can get above 12x speed ups, so orders of magnitude speed ups with regarding the message length. So here, what I'm showing again in the middle, that this proposal of ours, that how our collaboration basically started, we fulfilled it successfully. So we were really happy about these results. So what are the conclusions for today? This novel neural network approach is in agreement with the layered radio model baseline, while it has a significant speed up in computational time, especially when the packet length is large, as you could see here in the previous slide. With this frugally deep environment, our Keras Python implementation is compatible to the existing OMNeT++ ecosystem, making this project potentially viable for future studies and relevant use cases. In the future, we are planning to continue the collaboration and expand our model to generalize to multiple Wi-Fi modes. As for now, I forgot to mention, but for now it is only compatible with a single specific mode, but it's just basically, with this architecture, I think it's just a matter of data. If you get other modes, data, I think we can figure out a method where we can combine all these Wi-Fi modes. But that's really for the future. These are the tools we used for this project, and thank you very much. If you liked our approach to the project, consider checking out our website, socials, and maybe even contacting us. If you have any data science, computer vision, or regular programming related problem, we are more than happy to help you. And thank you again for the opportunity. That's all.
Well, thank you. We have nicely filled our time slot, I believe. We are allocated until 14:30, and that's exactly now. But we have, well, yes, it was just that 5-minute delay was precisely calculated. So
yeah, we clocked it. So I don't know if you have any. We can start over if you like.
okay, how about Daniel? Do you have
No questions.
Okay. I have just one question. Have you known this Frugally Deep framework before this project as well, or?
No. It was a really big surprise for us. We really like this thing, so we learned a lot, and this was the part, this Frugally Deep environment, what we could learn out from this project as well. So we really appreciate it.
I am also happy that we found it, because we tried like 3 alternatives that did something very similar, and this turned out to be the one that were the best.
Oh, nice. We are always happy to help in any particular way we can.
This is also interesting to me, because I also used machine learning in OMNeT, and I used the TensorFlow C++ API, which also worked fine, but it always has the problem that you need this TensorFlow build, and building TensorFlow with the Basel build system is not fun.
Yes, that is exactly why we chose to not use that, because we have to bundle this all together with OMNeT, and if it's possible to just, if you think about it, we have to do like a few matrix multiplications, so that shouldn't warrant like a multi-100 megabyte framework. Okay, sure, it runs on the GPUs and accelerators or whatever, but that's not really needed here. So it is fortunate that we found this little tiny simple library.